Welcome to my class. In this series of lectures, I will be discussing about different aspects of network theory. I will start with fundamental concepts of circuit elements and slowly I will move to the advanced concepts of circuit theory. Being an electrical or electronics engineer, it is very important to have a good knowledge of network theory. In this series of lectures, the laws, the theorems or different theoretical concepts that we will gain, they have wide applications in practical life. Whether you go for higher studies, whether you join academics or industry. In this series of lectures, I will try my best to explain the concepts in simple words. I hope you will enjoy the classes and you will learn from these classes. The first class will be based on various types of passive elements that we use in electrical circuits. So let's get started. In an electrical network, if we classify that with respect to electrical power supply or consumption, then that can be broadly classified into two parts. Some elements which are called active elements and some elements they are called passive elements. Active elements are those elements which basically supply electrical energy to the electrical network. Or if we see that electrical element or component amplifies or enhances the energy level of a signal that passes through that element, then it also can be said as active element. As for examples, we can take vacuum tubes, batteries, generators, some semiconductor devices like transistor and op-amp. And passive elements are those elements in electrical network which don't generate power or energy, rather they consume electrical power or energy. As for example, we can say resistor, inductor and capacitor. These are the elements which don't generate any electrical power or energy in that electrical network, rather they consume that electrical energy or power. Now, in case of resistor, that electrical power or energy is dissipated in the form of heat, and in case of inductor, that is not dissipated, that is rather is stored in the form of magnetic field. And in case of capacitor also, that electrical energy is not dissipated, rather it is stored in the form of electrical field. If we take the example of transistor, it may seem that transistor, like a battery, it doesn't supply electrical energy to the network, but transistor can amplify the power of a signal that passes through it. So transistor is an example of active element. On the other hand, if we take the example of transformer, then in case of transformer, on both the sides of it, at primary side and secondary side, the power remains same. So transformer will be the example of passive element. So here transformer doesn't supply any power or extra power. Now the basic three passive elements in electrical network that we know are resistor, inductor and capacitor. Now if we talk about the property of a resistance, which is called resistance, then the resistance is the property of a material by virtue of which it opposes the flow of electrons or charges through the material. So resistance basically works as opposition. Now it is the opposition or it is the restriction towards the current that flows through that material. Quantitatively, resistance can be measured from Ohm's law, and that we know is the voltage drop across that resistor divided by the current that flows through that resistor. And we know that the unit of resistance is ohm. And also resistance can be represented as a product of resistivity and the length of that material or conductor divided by the cross-sectional area of that conductor. So this is how resistance is dependent on the length and cross-sectional area of the conductor. So if the length and cross-sectional area changes, the resistance of that conductor will also change. Now rho here is the resistivity or specific resistance of that particular material, and the unit of that resistivity is ohm meter. And as I said, that L here signifies the length of the conductor and A signifies the cross-sectional area of the conductor. Again, the resistance, it is not fixed, it varies with temperature, so it is not temperature independent. Now if we represent, or if we want to obtain the resistance value at any particular temperature, then that can be obtained from this relationship, where RT signifies the resistance at temperature T. Here R0 is the resistance at 0 degree centigrade temperature. 1 plus alpha T, as we can see, is multiplied by this R0, where T is the change in temperature and alpha is the temperature coefficient at 0 degree centigrade, and T is the temperature at which we are basically finding the resistance value. Now there is a property, when we talk about resistance, there is another property called conductance, and conductance is just the reciprocal of resistance. So conductance, as we can see here, it is represented as 1 by R. So it is the reciprocal of resistance. So if resistance resists, restricts or opposes the current flow, then conductance helps the current flow. Unit of conductance is just opposite to resistance. So if the unit of resistance is ohm, then it is also symbolically is written as the reverse of ohm, and it is called mho. Is just also is read in reverse order, MHO. So it was OHM, it is MHO, and it has another name also, the unit of conductance, and that is also Siemens. Now conductance, between conductance and conductivity there is a relationship, or we can say conductance also, like resistance, it is not independent of length of the conductor, cross-sectional area of the conductor. Rather, conductance of any conductor is related to them, like G is equal to, here we can see sigma, where sigma is the conductivity or specific conductance of that conductor or material, that is multiplied by the cross-sectional area of that conductor divided by the length. It's just reverse of this formula that we have seen for resistance. Now the unit of conductivity again is the reciprocal of the unit that we have seen for resistivity. So for conductivity, the unit is 1 by ohm meter, and 1 by ohm is mho or Siemens. So the unit is Siemens per meter. Again, as I said, that resistance, it consumes power as it is a passive element, and it is dissipated in the form of heat across the resistor. Now the power absorbed by a particular resistor, it is voltage drop across that resistor multiplied by the current flow. So if the power absorbed, P is equal to simply V multiplied by I, and from the Ohm's law we know V is nothing but IR. So it can be also expressed as I square R. So if power absorbed by a resistor, if we want to represent that in the form of current, then it will be I square R. Otherwise, if we want to represent power in the form of only voltage, not in the form of current, then V and I, the current will be this time replaced by the voltage. So it will be V square I. So by using either one, we can represent power absorbed by the resistor. Now we know that power is the work done per unit time, and energy or work are taken as equivalent to each other. So if we want to obtain the energy, how much electrical energy is dissipated in the form of heat by that resistor, then it can be easily obtained by using the formula of power. So here the power will be taken as energy per unit time. So energy will be power multiplied by time. So that's what has been used in this formula, power. Then dt here represents the small amount of time for which that power was absorbed by the resistor. Now if it is for long duration of time, then that small amount of energy dissipation will be integrated over a long period of time. So small energy dissipation, we can say, will be added together to get the total energy dissipation by that resistor. So that's why here we have used the small energy dissipation P multiplied by that small time dt, and then we have integrated over a longer period of time, which is from 0 to this much time t. And after as per the rule of integration, finally we are getting P multiplied by t. This is a definite integral, so after integrating, if we put the limits, then finally we will be getting P multiplied by the t, the total time of that time duration. Then P we can represent in the form of I. If we do that, then it will be I square RT, and if we represent in the form of V, voltage drop, then it will be V square by R multiplied by that time taken. Next we will see the next passive element that we frequently use in electrical network, or we can say the AC circuit. This inductor is an AC component, and the property that we have seen in case of inductor, which is called inductance. And inductance is the property of a material, we know that by virtue of which it opposes any change in magnitude or direction of electric current passing through that conductor. So it is again works as opposition towards the current, but this time it is not the directly current, rather it is the change in magnitude or direction of electrical current. So in inductance is also opposition like resistance, but this time this opposition works towards the change in magnitude or direction of electrical current that passes through that conductor or inductor. Now we know that by inductor simply we understand that it is a coil having a few turns. So if a coil or a wire of finite length is twisted into a coil having some turns, then it forms a simplest inductor, as we can see in this diagram. Now we know that from Faraday's law that when a conductor is placed in a magnetic field, then a current passes through that conductor, because a voltage first is induced in that conductor, and when that conductor completes a path, then a current is induced in that circuit, or the current flows. And the inductance value, if we want to calculate for that particular inductor, then that can be found from this relationship where L signifies the inductance of the inductor. We know that we have two types of inductances, concept of two types of inductances. One is self-inductance and the other one is mutual inductance. I will come to that. But whatever it is, in general, the inductance value is related to the current that flows through that inductor and the flux which is generated in that magnetic field, and also the number of turns in that coil or inductor. And it is N, which represents the number of turns in that coil multiplied by the flux associated with that coil or flux that flows in that magnetic field, divided by the current that flows through that coil or inductor. Now the unit of inductance is Henry, and 1 Henry is measured as 1 Weber turn, where Weber is the unit of flux, and turn here represents the number of turns of that coil. So here it is 1 Weber turn divided by 1 ampere. We know the ampere is the unit of current. So for 1 Henry, Henry is the unit of inductance, and 1 Henry is the measurement of 1 Weber turn divided by 1 ampere or per ampere, we can say. In case of mechanical system, we have seen, or we have the idea of inertia, or mechanical inertia for a particular mechanical body. Here the inductance is also equivalent or analogous to that inertia, or it is also said called as electrical inertia. Because of this electrical inertia across any inductor, when we connect any voltage source, the current through that inductor doesn't reach to maximum value at that instant when we are connecting that voltage source or supply. Rather, it gradually increases. Again, when it reaches to a to the peak value or maximum value the current through that inductor, then suddenly if we disconnect the voltage source or supply from that circuit or from that inductor, then again suddenly the current that flows through that inductor will not be zero, rather that current value will gradually decrease and then finally will become zero. So this inductance, this property works as electrical inertia for that inductor. Now from Faraday's second law, we know that the induced voltage that we talked about in case of Faraday's first law, this induced voltage can be found from this relationship, where the induced voltage E is equal to, it is the rate of change of flux that flows in that magnetic path or magnetic field multiplied by the number of turns. So it is magnitude wise, value wise, it is N multiplied by d phi by dt, and along with this, as we can see here, we have negative sign. Now we know that when this induced voltage will supply a current, means this induced current, when we will have a complete path in that electrical network, so we will have induced current that will flow through that electrical circuit or network. Now because of that current, it will also produce a magnetic field, and that magnetic field will also induce an EMF, and that EMF will also produce some current that will flow in that circuit, and this time this current will flow in opposition or in opposite direction of the main current, or we can say the current which was caused. So here the effect, here in that circuit we will be having finally two currents, one current that is the cause for which this EMF was induced, and the current that is finally is generating because of that induced EMF. These two currents will work opposite to each other, and that's why this negative sign comes. So we can say here the effect opposes the cause, and this is explained by Lenge's law. From this relationship, now if we replace phi, we can, here the phi value will be L multiplied by I divided by N. So if we replace phi, then L is the inductance which is constant for that inductor, and then I is the parameter which is dependent on time, so that changes, and also N is fixed, that is the number of turns. So for any inductor or coil, that will be also fixed. So here in place of phi, when we will put Li by N, L by N will be constant, that will come out of that differentiation, and it will be finally di by dt, and already we have here one N, and we will be getting L by N parameter, and it will be di by dt, and that will be equal to the induced EMF. So finally this N and N will cancel each other, so it will be minus L then di by dt. So either way we can represent the induced voltage across that inductor, either by this relationship where we have the rate of change of the flux that flows in that magnetic field, or we can represent by the rate of change of current that flows in that electric field. Now inductance is another way, can be said as or can be explained as 1 Henry when current through a coil or conductor changes at the rate of 1 ampere per second, inducing 1 volt across that coil. So this, in this definition or explanation of inductance having value 1 Henry, can be explained from this relationship, where the changes, as it is written here, the current through a coil changes at the rate of 1 ampere per second. So that means it is talking about this di by dt inducing 1 volt across the coil. So it is talking about this VL. So basically it is L will be VL divided by di dt. Now, as I said, there is a concept of two types of inductances: self inductance, which is because of the current that flows in that particular inductor. And suppose in any electrical network, if we have more than one inductor, so there will be a concept of mutual inductance as well. Mutual inductance, mutual, the term itself explains that there is an element or entity which is more than one. So in case of mutual inductance, we will get some result because of the cause from other side. So as we can see here, the relationship of, or the definition of mutual inductance, how it is expressed as M suffix 2 1. Here 2 signifies the second coil. So here it is the mutual inductance of the second coil because of the current and flux in the first coil. So that's why 2 1. So it is the value of the mutual inductance of the second coil, but because of the flux that flows in the magnetic field of the first coil, or because of the first coil, and also the current value that flows in that first coil. So the cause, the current and flux, they will come from the first coil, and the effect that will be in the second coil. And here the number of turns, that value will be linked with the second coil. So formula wise, it is M21 will be N2 phi 1 by I1. Similarly, we will also have mutual inductance in the first coil as well. So it will be M1 will be represented by M1, and this is because of the current and flux value of the second coil. So 2 suffix 2. And in the expression, since this mutual inductance is linked with the first coil, so here the number of turns will be N1, and this is because of the current and flux value of the second coil. So here it will be phi 2 divided by I2. Now the expression of induced voltage that we have seen earlier, that is because of this inductance value. So here when we have two coils in that circuit, so the voltage will be induced because of the self inductance of that particular coil, and also because of the mutual inductance of the other coil. So here finally in the expression of induced voltage, we will have, in place of simply L di by dt, it will be, if it is suppose the induced voltage is associated with the first coil, then it will be L1 di1 by dt, because it is self. So here directly the induced voltage and the current, they will be directly linked with that particular coil, and also the inductance value. So if it is V1, then it will be L1 I1. And in case of mutual inductance, it will be because of the mutual inductance of the first coil, that mutual inductance is because of the current value and flux value of the second coil. So here M12 that we have seen here, and the current value that is, as I said, is coming from the second coil, so it will be di2 by dt, and in place of M12 we will be replacing this value. Similarly, if it is the induced voltage of the second coil, then that will be because of the self inductance. So in that case it will be L2 di2 by dt, and that will be because of the mutual inductance. When it is, then it will be M21, and mutual inductance, for that mutual inductance the current and flux value will be linked with the first coil, so it will be di1 by dt. So this is how we calculate the induced EMF when we have two coils. Now these two coils can be connected in series or parallel, or it may be that there is no direct electrical connection between those two coils, as we know we see in case of transformer. Now next, as I have already said, that since inductor is passive element, so power will be absorbed by the inductor, and this time the power will not be dissipated, rather it will be stored as or in the form of magnetic field in case of inductor. So power absorbed, again it is simply the multiplication of the voltage and current, and this is since it is AC component and it is used in case of AC circuit. So there we will have different types of voltage and current that I will explain in my future lecture. Here the small v and small I, they represent the instantaneous value of voltage and current respectively. Instantaneous value of voltage means the value of voltage at a particular instant, because here the voltage and current are changing in nature. So with respect to time, it always changes. So it doesn't have a fixed value that we see in case of resistance, where the voltage and current value are constant, DC voltages, but DC voltage and DC current. But it is AC, it is alternating, it is changing, it changes with time. So when we are focusing on the voltage and current value, that will not have any fixed value, or rather it will be there will be the values of a particular instant. So now here, as we have seen, the V induced voltage is L di dt. So that value and multiplied by the current value will give us the expression of power, or the measurement of power which is absorbed by the inductor. Now if we want to obtain that how much energy is absorbed by the inductor, like we have seen in case of resistor, it is the simply is the power which is absorbed per unit time. So it will be or it will be multiplied by that small amount of time during which the power was absorbed. And then if we want to find the energy absorption, that if we want to measure, then it will be those small energy absorption will be added. So that's why it is integrated over a longer period of time. So it is from 0 to t. T can have any finite value, and we know that integration is kind of summation only. So it is continuous summation. So after, if we follow the rule of integration, then finally we will be getting this value half Li square. So here we can see that energy absorption in case of inductor it doesn't depend on voltage, rather it depends on the instantaneous current value that flows through that inductor. So we can say here that even if the voltage is very small or negligible, but we will be getting energy value across that inductor, or in that magnetic field produced by that inductor, and that is dependent on the current value. Even though the voltage is almost zero, but still it can store finite amount of energy in that magnetic field. And as I have already said, that because of the electrical inertia, that property, current through any inductor doesn't change abruptly, or it doesn't go to the peak value suddenly, rather it gradually increases. So initially when we connect a supply voltage across that inductor, or we complete the circuit, initially at that moment the current that flows through that inductor is zero, then gradually it changes, gradually it increases. So initially an inductor behaves like open circuit, as if no current is flowing through that inductor, and gradually it increases and reaches to peak value. So when it reaches to peak value, then there is no change in current. So di by dt, if we take, since there is no change in current value, so di by dt, this factor will be 0. So that means the voltage which will be induced across that inductor, that will have a 0 value. Now since the voltage across that inductor is that has 0 value, so it will work as short circuit. So we have to remember that an inductor initially behaves like an open circuit, and finally it behaves like short circuit. This is an important phenomena of an inductor. Next we will see another important passive element, or AC component, that we see in electrical circuit, and that is capacitor. Now the capacitance is the property of a capacitor, or of a material, by virtue of which we can measure that how much electrical charge or electrical energy it can store within it. When we talk about capacitor, basically we know that across that, if it is a parallel plate capacitor, then on the plates of the capacitor the charges are deposited. So it is the measurement, the capacitance is the measurement that how much charges it can store on the plates of the capacitor. So capacitor basically it stores charges. We can also say that it stores electrical energy in the form of electric field that is produced or established by the two polarities of the charges on the two electrodes of it. and we know that the unit of capacitor is farad, and sometimes it is represented at millifarad or microfarad. 1 millifarad is 10 to the power minus 3 farad, microfarad is 10 to the power minus 6 farad. Quantitatively, it is the measurement of charge stored per unit voltage. So it is an important relationship in case of capacitor. C is equal to Q by V, where Q is the charges, the amount of charge which is deposited on the plates of the capacitor, and V is the voltage or instantaneous voltage value or voltage drop across that capacitor. So again, since this is an AC component and we will be using in AC circuit, so here the voltage and current will be expressed as instantaneous voltage and current. Now current that flows through the capacitor, so here if we write this way, that Q is equal to C multiplied by that voltage drop V, and if we differentiate both the sides with respect to time, then it will be C dV by dt. Now we know that this rate of change of the charge flow that is equal to the current. So in place of dq by dt we can write I, and C dV by dt we can write on the other side of that equation. So this is the relationship between the current that flows through the capacitor and also the voltage drop across the capacitor. This is also an important relationship in case of capacitor. Now the voltage drop across the capacitor can also be found from this relationship, and that is, here I will be multiplied by dt, and then this C will be, when it will come to the other side, this will be 1 by C. Now dV is the measurement of the small voltage drop or difference across that capacitor, and here, so if we want to get the total voltage drop, then it will be integrated, or we can say this small voltage drop will be added. So if we integrate, then dV will become V, and it will be 1 by C, and integration of 0 to 2t, where t represents the total time interval or time period for which we are measuring the voltage drop, and I dt. And here V naught is the initial condition that we are using, because when we work with capacitor, it may happen that initially the capacitor plates already had a few amount of charges. So since the plates had a few amount of charges, that means because of those charges there will be a voltage drop across the capacitor. So if already or initially the capacitor has charges and capacitor a voltage is some amount of voltage is dropped across that capacitor, then the final voltage, when we will be finding out, then in that expression we should also mention the initial voltage drop. But initially, if the capacitor was fully uncharged, in that condition, then the voltage drop across the capacitor will be 0. In that case, this V naught will have 0 value, and finally the final expression of the voltage drop across the capacitor will be only this much. Now, like we have done for resistor and inductor, if we want to get how much power is absorbed by a capacitor, that we can simply do by this expression. P will be the multiplication of the instantaneous voltage and instantaneous current. Now we have already seen that the expression of current that flows through the capacitor is C dV by dt. So in place of current, if we put this relationship, finally it will have this type of relationship for the power absorbed by a capacitor. Now if we want to know that how much energy is stored in the form of electrical field by that capacitor, then it will be simply the way we did for inductor. So it will be integration 0 to t p dt, and finally it will be half CV square. So here from this relationship we can say that even though there is no current or a very small or negligible amount of current is flowing through that capacitor, but still it can store a finite amount of energy in that electric field, because it doesn't depend on the current value. Rather, in that expression, as we can see here, it depends on the voltage drop across the capacitor. As I already said, that The capacitor doesn't dissipate that electrical energy, rather it stores in the form of electrical field. And as we have seen in this relationship, that C is dependent on the charges and the voltage drop by this relationship. So when if the capacitor initially is fully uncharged, then the voltage drop across that capacitor will be Q by C. So since Q is 0 and capacitance is the constant for a particular capacitor, so if there is no charge initially, then the voltage drop across the capacitor will be also 0. So we can say that capacitor initially behaves like short circuit, since the voltage drop across the capacitor is 0, and then gradually the charges will be accumulated on the plates of the capacitor, so the voltage drop across the capacitor will gradually increase, and finally it will reach to its peak value or maximum value, after which there will be no change in the voltage value. So dV by dt, that factor will be 0. So if dV by dt is 0, then the current that flows through the capacitor will have 0 value. That means finally through the capacitor, when the capacitor has reached to its peak value, the voltage drop across the capacitor, and after that there is no more change in the voltage value, the current flown through the capacitor will be 0. So we can say that finally the capacitor will behave like an open circuit. So it is just the reverse of inductor, opposite to inductor. In case of inductor, we have seen the inductor initially behaves an open circuit and finally it behaves as short circuit. But in case of capacitor, initially it behaves as short circuit and finally it behaves as open circuit. So this was the explanation of the very basic passive elements or very basic components in case of electrical circuit: resistor, inductor and capacitor. In my next lecture, I will discuss about the different types of energy sources that we use in electrical network, because that is also an important element in case of electrical network. So with this, I end today's class. Thank you.